There we go. Okay, so here's a few remarks that I should have made perhaps yesterday. On the other hand, I mean, if I try to explain everything in advance before doing examples, then it doesn't help that much. So the first remark I want to make, and this is something I was using all the time in my examples, and I realized it might not be um, obvious what I was doing. So let's say that you have to show a statement of the following form. So you have a statement of the form P implies Q. Okay. So if you look at what I did, okay, so I proceeded as follows. So what you do is you assume P. So you assume that P holds, that it's true, okay, right? And then what you do is you deduce Q from that, okay? So you start with P, you suppose P is true, and you deduce Q. From this whole thing, you get that if P, then Q, right? So from this, so that's how you prove this. So from this, we get if P, then Q, right? So that's the technique, okay? So look up the examples, look at the examples yesterday, right? All of those that had this shape, if P, then Q, I proved this way, okay? Second remark that I want to make is about statements which look like this. For every x, P of x. Now, P of x would be very complicated. This is the shape. So there's a universal quantification. So I have to show something is true, and there is some universal quantification, okay? If you look at how I did this in the examples, and this is something I know a lot of people have trouble with at the beginning. So what you do is you take what we say, you choose an arbitrary x, but the concept of arbitrary is really fundamental here. You don't choose an actual x, that one, right? You have to take a general x. So you take an arbitrary generic, if you want, x, and you prove for that x P of x, what you want to prove, okay? So if you make no specific hypotheses on x, it's arbitrary, then it means that the statement has to be true for any x that you can take. So we conclude that the result has to be true for all x, right? In other words, for all x, P of x. Okay. Again, this is something I mean, as I do more examples, you'll see a little bit how this works, but you've seen this before also, but it's a question of getting used to. I've heard sometimes the students say, oh yeah, we take a random x. Random is not the right word. Random in mathematics has a very precise meaning, and it's not that. This is an arbitrary x. It's any x. Okay, there's no distribution. There's no probability distribution here. Third comment I want to make, because you might be curious at this point, you say, okay, so now we have this for all x P of x. What about there exists an x P of x? And I'll talk about that a little later today in more details with examples to show there exists an x P of x. If you want to show something like that, the best way is you give the x, right? So the best you can do is to actually produce the desired x, right? So for example, in a very silly example, let's say you want to prove there exists an x such that x plus 5 equals to 2. Let's say you want to prove that. How you prove that? You say, well, take x equals 2 minus 3. So proof x equals to -3. That's the proof. You don't need to do anything. I mean, right? You plug in -3 in there and that's it. Okay. Unfortunately, that doesn't always work. Okay. Alternatives. There are many, and I'll show you. So what we'll call non-constructive proofs. So it's possible to show the existence of something without actually providing it. Now, you remember yesterday I talked about this bunch of mathematicians who were against the use of proof by contradiction. A part of that bunch was against that precisely for this reason. So in their mind, their philosophy was that if you have an existential statement, then to prove it, you should always construct and provide the actual witness. And so they were against non-constructive proofs. I mean, from a philosophical point of view, I can understand, but from a logic or mathematical point of view, I don't find that very interesting. But I'll show you some non-constructive proofs in about 15 minutes. Okay, so see examples later. Okay, all right. So I'm going to move back to section 1.7. Okay, so 1.7 continued. So we were looking at proofs by contradiction. Proof by contradiction. So what is that again? So you want to prove P. Okay, some statement P. So what you do is you say, okay, suppose not P. Okay, so suppose things don't go well at all, and not only is P not true, I mean, not P is true, not P is true, same thing, right? So, and what you do is you deduce from this some statement Q, right? Q, which is false. Okay, so if starting from not P, you deduce something correctly, of course, something false, the conclusion of this is that P has to be true. So conclusion, P is true. Okay, so that's the strategy of a proof by contradiction. Okay, I did an example yesterday showing that every integer is, no integer can be both even or odd. I'm going to do another example, which is probably the most famous, not only the most famous proof by contradiction, but perhaps the most famous mathematical proof of all time. So I'm just going to take actually a different page for this. So here's a theorem that I'm going to prove. And honestly, I mean, this won't sound right, but if you have to understand one thing in this course, I mean, hopefully more than one, but if you have to, in 20 years, remember one thing from this course because you're doing something completely different, I'd say that would be a good one, okay? So here's the theorem. The theorem is that root 2 is irrational. So we're going to prove this, okay? So try to follow every little step that I'm doing. If you can do that, you'll get to the end and you should be able to believe that root 2 is an irrational number, okay? If not, you reread it later until you get it, okay? It is not super hard, okay? There's a couple of little tricky things in there that we'll pay attention to. This goes back to Euclid. So this is old. Okay, so this is a very old result. And the wonderful thing about math, and that's one of the reasons I like it so much, is that you see this thing was proved a long time ago and it's still true. So once you get it, once you understand this, it'll be with you forever. Nobody can take it away. No, nobody's going to come up in 25 years, say, oh, you know, that thing, no, it's not true anymore. Now we're somewhere else. No, root 2 is irrational. End of story. That's it. Okay. So here we go. So how do you show that root 2 is irrational? What does it mean, right? You want to show that root 2 is not rational, right? So to show square root of 2 is not rational, and a rational number is a ratio of two integers, p divided by q, where q is non-zero. So we're going to do this by contradiction. Okay, so this is a proof by contradiction. So how does this work? So I'm going to suppose that root 2 is in fact rational, and I'm going to deduce nonsense from that. Okay, so suppose root 2 is rational, we will deduce a contradiction, right? So something false. Okay, so root 2 rational means what? Okay, so it means that there exist two integers, q not 0, such that root 2 is equal to p divided by q, right? So that's what it means for root 2 to be a rational number. Here's the first somewhat tricky little thing that I'm going to do here, okay? And if you have trouble with it, raise your hand. I should get the chat, sorry. Put it over here so I see, good. And so just let me know if this doesn't work for you, okay? So you know that if you write a fraction, you can reduce it, right? You can simplify a fraction. Everybody's comfortable with this. So if root 2 is a fraction, right? So it's p over q for some integers, I can certainly assume that this fraction is reduced. It's as simplified as possible. So we assume, and I'm going to say here without loss of generality, and this is something that comes back often. So I'm not adding an extra hypothesis here, but p over q is reduced. Does everybody understand what I'm saying? So let's, okay, so it is not, 3 over 6, which reduces to 1/2. That's what I mean by reduced. Is that okay for everybody?
Yeah.
All right. So I say if it's a fraction, if root 2 can be written as a fraction, I can certainly write it as a reduced fraction. So you write it as a fraction, you reduce it. Eventually you'll get p and q. So what does it mean? It means p and q don't have any common factors. I can't simplify, right? So cannot simplify. Cannot be simplified. Okay, great. So let's go here. So what am I going to do? So you can probably guess, I'm going to play a little bit with this. So if I've got root 2 equals p over q, I'm going to get that root 2 times q is equal to p. I'm multiplying by q both sides. I'm just going to do some elementary arithmetic now. And so if I square both sides, I'm going to get 2q squared equals 2p squared. Yes. Okay. So what does it mean? So p and q are integers. Here, everything we're looking at are integers on both sides. 2q squared equals to p squared. What can I deduce from this about p squared as an integer? It's twice some integer. It is even, right? P squared is an even integer. It's twice q squared, right? If you remember what we did yesterday, what can we deduce from the fact that p squared is even? About what can we say about p? It is
Even as well.
Also even.
yes, correct. All right, so p is an even integer. We know that, we've proved that before. So if p is even, it means it is twice some integer. So there exists some k integer such that p equals to 2k. I'm going to replace that in my equation. Okay. So 2q squared equals to 2k squared, which is the same as 2q squared equals to 4k squared. I can divide by 2 both sides. So q squared equals 2k squared. I'll bet some of you can see the finish line from here, but if not, it's okay. So q squared is 2 times k squared, hence k squared is even, yes. So q squared is even. Same as we did just a few seconds ago. If q squared is even, q is even. Do you see the problem? Good. It's a good problem for us. We're happy.
Means that the fraction p over q is not reduced since both are even.
Yep. So I've argued. So I started by saying I start with p over q being reduced. I can do that for sure. If there's p and q exist such that root 2 is p over q, I can choose p and q such that the fraction is reduced. So it's not possible for both of them to be even. But then I computed and I found that whatever happens, p and q will always be even, both of them. That's not possible, right? So I have both p and q even, but not both even. That's a contradiction. So that's a contradiction. Okay, so since p over q is reduced, so we're done. That's it. Nice and simple, very cute, very, very elegant. If you didn't get everything, it's okay. Just reread it step by step, okay? If that doesn't work, call the doctor, call me up, okay? We'll fix it. But if you, it would be really cool if everybody can go from top to bottom here and just see it like, yeah, I get it, okay? That would be really cool. So, so root 2 is irrational. There you go. That's the proof. Wonderful. Hope you enjoyed it. Okay. So let's move on to a few other technicalities, unless there are questions. Okay. Proofs of equivalences. Okay, so there's often need to prove statements of the following form. So proving a statement of the form P if and only if Q. Essentially, there are two ways to do this. The most common way of doing this is as follows. If you remember, P if and only if Q is logically equivalent to if P then Q and if Q then P, right? So P if and only if Q is logically equivalent to P implies Q and Q implies P. Right? So it means that if you show if P then Q, and then you show if Q then P, you've shown P if and only if Q. So show separately these two things. So this and this separately. This is probably the most common way of showing a statement like that. Sometimes it's possible to do, sometimes direct proof of an equivalent, I mean of an equivalence like this is possible. And I'll show you an example. Okay, so here's a very simple little example. Well, the first example is for every integer, don't do it like that. For every n, n is odd if and only if n squared is odd. This is for integers, right? If you remember, we did, oops. Okay, if you remember, we proved both directions separately, right? So we proved this and this separately, right? So that was like what I said, the most common way of doing this. That's what we did. So the proofs are not the same, right? They're different in a sense, okay? Here's another example. We're asked to prove that for every m and n integers, m squared equals to n squared if and only if m equals to n or m equals to minus n. Now, another thing I want to say is when you're writing on, writing on a proof is like, unless it's like super easy, usually you'll have to, oh, that's okay. Thanks. Thanks for saying so. Often you have to mess around because there's writing out the proof, but there's also figuring out what it is, right? So this is like problem solving. You have to solve if you don't know the proof in advance. So you're messing around and eventually you sort of understand, okay, this is how it works. And then you write it up, right? And it's not necessarily always in the same order, direction, okay? So here, I could show, okay, let me show you how my brain would work for something like that. So on one side, I'm going to put like my brouillon, the scratch paper, and then how I write it up, right? Okay, so here's on the left hand side will be like what I'm messing around to figure out why this is true. Okay, so I look at this and I say, okay, m squared equals to n squared. That would be the same as m equals to n or m equals to minus n. Okay, so I'm trying to sort of see the connection here. Well, here's probably what most of us would do, right? We'd say, okay, let's write m squared equals to n squared. And you look at the right-hand side, it sort of gives you a hint. You say, okay, that's the same thing as m squared minus n squared equals to 0, right? That's the same thing as if you factor it out as m minus n, m plus n equals to 0. And there you go, right? Basically, we see what's going on. Okay, so we see it now. Okay, so now I need to write it up properly. I have two choices here. I can either do one direction and the other, or try to do it as an if and only if. Okay, let me start by doing it as two separate directions. And it's a good logic exercise, I think, to think of it this way. So, so the proper written proof. Okay, so I'm going to do this direction first. Okay, so suppose that m squared equals to n squared, then, and I'm going to do exactly what I did on the left-hand side. I know exactly what I'm supposed to do. Then m squared minus n squared equals to 0. So m minus n times m plus n equals to 0. And I know that the product is 0 precisely when at least one of them is 0. So m minus n is 0 or m plus n is 0. In other words, m equals to n or m equals to minus n, which is what I wanted, right? So I started with m squared equals to n squared, and I conclude from that m equals to n or m equals minus n. So I've got that direction, right? Which is different from the other direction. You have to be careful, okay? So let's do the other direction now, which is actually easier. If easier than that is possible, I don't know. So let's just do the other direction like that. Suppose m equals to n or yeah, this is actually something I should have discussed maybe before. But anyway, I have an or and I need to conclude something. How do I do that? Well, you have to do them separately. Okay, so case 1, m equals to n, then obviously m squared equals to n squared, right? You square both sides. It's obvious. Case 2, m equals to minus n. Well, you square both sides again. And that's it. Right? But you see there's a sort of different flavor in both directions, right? I could have done it as a sequence of if and only ifs, okay? Which is more what I did on my scratch paper, okay? Sorry, I'm already, also correct would be as follows, okay? So it's a sequence of equivalences, what I call the direct proof. With harder problems, this is very rare that it works. It's just very elementary, it'll work, but it's rare that something, if it's not quite elementary, it's very rare that this is going to work, okay? So, so here we go. So m squared equals to n squared. This is equivalent to m squared minus n squared equals to 0. You see what I mean here? Because if m squared is equal to n squared, then of course I can subtract both sides. And if m squared minus n squared is 0, I can add n squared both sides and get back what I wanted, okay? So I can go either way, it's the same. Now I can, of course, rewrite this as m minus n times m plus n equals to 0. This is completely equivalent, which is equivalent to one of them is 0. Right? And I'm just going to rephrase that and I'm done. So this is m equals to n or m equals to minus n. Okay? So that's another way of doing it. The only thing I'm saying is this second proof here, in general, it doesn't happen so often that you can do it this way. Okay? You often have to go both directions. Okay? Okay, on this topic, one last thing. I'm gonna switch to the slides here. This too much stuff. Okay, all right. So, okay, so this is exactly what I just talked about. So you have a if and only if. Most common way of doing it is you show if P then Q, and if Q then P. You show these two things separately, okay? Now, often you will see, and if you go back, I don't know if in Cal, I don't know if in the Stewart book you see anything like that, but anyway, this is a very, very common kind of theorem where they tell you the following are equivalent, and then they give you several statements, which here I put blah, 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 blah. It doesn't matter what they are, okay? What does this mean? It means that they're claiming that it's an if and only if between any two, okay? So they're claiming that this statement, 1 if and only if 2, 2 if and only if 3, and 3 if and only if 1, okay? So that's a lot of proofs, right? But in fact, you don't need to show all the equivalences at every step. You don't have to do 6 different things, right? Because you can go in a circle. That's the one of the tricks. That's what I wanted to tell you. So let's say these are P, Q, and R. You're trying to show that P if and only if Q, Q if and only if R, R if and only if P. But all you have to do is this: show, for example, if P then Q, if Q then R, and then if R then P. Because this thing is transitive, because if P then Q and if Q then R, then you get if P then R, right? So you're going to get every single direction because you're going in a circle like that, okay? So this is a very, very standard way of doing this. So if you have you have more than 2 equivalent statements, you go into a circle, right? That's the shortest way of doing this. So here's an example. It's unfortunately a bit tough to read. So I'm going to switch back to my black whiteboard to do this. I'll just write it out here. So theorem, or I'm not going to call it theorem because it's sort of, so just an example, prove that the following are equivalent. One, or for every x in R, x is rational. 2, x over 2 is rational, and 3x minus 1 is rational. Okay, so I'm going to switch back. Okay, so I'm asked to prove that these 3 statements are equivalent. Notice I wrote TFAE. This is classic abbreviation. The following are equivalent. Okay, so what I'm going to show is this. I'm going to show that 1 implies 2, then 2 implies 3, and 3 implies 1. So this will show if and only if in between each 2, okay? So let's start with 1 implies 2. If x is rational, then x over 2 is rational. So again, what does it mean? I assume x is rational. That means there exists integers p and q, q not 0, and x is equal to p over q. So x over 2 is equal to p over 2q. So that's an integer divided by an integer, which is not 0. So that's it, right? This is clearly rational. Okay, 2 implies 3. They're all easy. 2 implies 3. X over 2 is rational. Still, okay, you have to be careful. Now once you're at level 2, you don't know that x is rational anymore. You cannot assume that x is rational. I mean, this is so very elementary that it can get confusing because, I mean, it might be obvious that if x over 2 is rational, so is x is also rational. But from a formal point of view, be careful. Once you've done 1 implies 2, now you're doing 2 implies 3. Whatever happened in 1, you can't use that anymore. It's not in the discussion. This is important. Okay, so we have x over 2 is a rational. That means, and I'll use p and q again. P and q are integers. Q is not 0. X over 2 equals p over q. And I want to show that 3x minus 1 is rational. So 3x minus 1 is rational. What is that? Well, we have, I should have used some scratch paper here first. So we have x equals 2p over q. So 3x minus 1 is 3 times 2p over q minus 1, right? I want to express this as a fraction. I'm back, yes. So this will be 6p over q minus 1. And I take a common denominator. So this is 6p minus q over q. And that's a rational, right? Because 6p minus q is an integer, q is an integer, which is not 0. Bingo. Okay. And finally, the last step is to loop the loop. 3 implies 1. So I want to show that if 3x minus 1 is rational, then x is rational. Okay, that's what I want to prove. So my assumption is 3x minus 1 is rational. That means there exist integers p and q. Q is not 0, such that 3x minus 1 is equal to p over q. I wanted to do something about x. I'm going to solve for x, right? So 3x is equal to p over q plus 1. So x is equal to 1/3 p over q plus 1. If you're thinking, wait, he's using fractions all the time here. Yeah, because these are results about rational numbers, not integers. So that's why I'm obviously going to use fractions. So finally, x will be p plus q over 3q. I skipped a little step here, but obviously you can do that. So, and this is, again, clearly a rational. So we're done. We've done all three. Okay. Hopefully you see the idea. So the main idea of here, I just wanted to do an example, is loop the loop. Now, for these implications, you might have to use contrapositive, things like that. It's possible, right? That's done. That's wonderful. This is done also. Wonderful. Okay, so I'm moving on to 1.8. For me, there's really not much difference between 1.7 and 1.8. It's just like one big section for me. Okay, so so that you see where the stuff is coming from, I'll just write this so you'll know. So proofs continue, because a lot of the examples that I'm considering come from the book. Okay. And again, it's divided into strategies and things like that. But mostly the point is for you to see examples, right? So we learn by mimicking. Okay, so here's a sort of more high level proof strategy, but hopefully it makes sense. So here's a remark. They call it proof by cases. So let's say you're asked to show, or you have to prove something that looks like this, to show a statement of the following form. So it's P1 or P2, or you have a disjunction like that of various statements, and you want to show this, if this, then Q. Okay, this is quite common. We just saw, see example earlier, m equals to n or m equals minus n implies m squared equals to n squared. Okay, so that's exactly of this form. So when you think about it, if you want to show that a whole big OR like that implies Q, what do you need to do? So what this says is if P is true, if P1 is true, then Q is true. If P2 is true, then Q is true, and so on, right? So this clearly means this. I mean, it's going to look weird. I mean, but think about it, right? So this statement says, as long as one of these statements is true, I should be able to conclude Q. Okay, so it means that P1 should be strong enough to conclude Q, right? Because then the left-hand side is satisfied. If P1 is true, then the left-hand side is true. And P2 implies Q. And it's an and, right? So it breaks up as an and of statements. Right? This is logically equivalent to this. Think about it, okay? So the left-hand side is true as long as one of them is true, and that should be sufficient to conclude Q. So you have to show all of these separately, okay? Which is exactly what we did in our example over here, right? So we said if m is equal to n, then I should be able to show m squared equals to n squared, and if m is equal to minus n, I should be able to show m squared equal to n squared. So you have to do it for each one separately, okay? So that's an important remark, higher level. Here is, okay, so now let's just jump into some examples, which will use all sorts of, okay, so here's an example, not of what I've illustrated. So other, okay, so here's one. Show that n plus 1 cubed is greater or equal to 3 power n for every n less or equal to 4 integers, positive integers. So notice I've used that little shorthand for every n less or equal to 4. Okay. Now, if you just look at this and you say, okay, wait a minute, I need to show this inequality. If you start messing around with the inequality, right, like high school style, you're totally wasting your time because you'll never, ever get anywhere with it. Because you see, this thing is true for very few numbers. It's not true for all numbers. So if you try to show it symbolically, you'd be showing it for every integer n, right? Which brings me to, there's another awful mistake that I don't want you to be doing. Yeah. Okay, so don't do this. I don't know where this comes from, but I've been seeing this for decades. It comes from high school. Something happens in high school, and it's not like I probably did. I'm sure I did the same thing as a student at some point. I don't know what makes us do it. Okay. If you start with what you want to, I mean, this is like a typical bad mistake that I see in calculus when we're trying to show trig identities. And this is a classic thing where you start with the identity you want to show, and you conclude 1 equals to 1, and you say, there we go, that's the proof. And that is bad. It doesn't prove anything, because I can prove 1 equals to 1 starting from 0 equals to 1. So I'm not going to get anything good like that, okay? So what you don't want to do is something like n plus 1 cubed greater or equal to 3 power n, and so mess around with some algebra, and eventually get, let's say, this. Suppose you do that. What you have proved is if this thing is true, then n has to be less or equal to 4. But it doesn't prove that it is true for n less or equal to 4. It means at best it's true for n less or equal to 4. Hopefully, okay, so this would show if n plus 1 cubed greater or equal to 3n, then n greater or equal to 4. What we want to show is the other direction. We want to show it is actually true when n is small, is between 0 and 4, 1 and 4. Okay, so this is really, really something to avoid, right? So this is, be careful, okay? So what you want to show, so actually the proof is much simpler than that, right? So I need to show this thing for n equals to 1, 2, 3, 4. What do? Plug in 4 cases, end of story, okay? So the actual proof is this, just plug in. That's it. That's the proof. Right, so I won't do it. I won't insult your intelligence. Just plug in n equals to 1. You get 8 greater or equal to 3, and so on, right? So, and I'll just do the first. N equals to 1. You get 8 greater or equal to 3. It's true. N equals to 2, and so on. That's it. Okay. All right. All right. All right. All right. Here's another one, similar, more interesting. I mean, please jump in if you have anything at this point. I'm so alone.
I'm not sure I understand the thing about the don't do the algebra.
Yeah. Okay. Yeah.
Why not? Why can't we do it?
Okay. Sorry, I just thought about this right this moment. I hadn't prepared this, so this is not the best example. Can I find a better example?
So wouldn't that be bidirectional implication?
Yeah, so that's a good remark, but it is getting subtle. If you manage to do an if and only if, then that's correct, which is yeah. But it's stronger than what you're actually trying to prove, so it might not be true. So, so here it is possible that this inequality is valid for some other values of n. We're just not asked to show that. It turns out, I suppose, that it is not true for n bigger. I mean, it's not true for 5, and it's probably not true for bigger than 5. But no, good point. If in your deduction you're using if and only if, perfect, because you have that direction. Okay, so what I'm saying is okay, I'm sorry I can't answer your question, so because I improvise this, but I will show you an example on Thursday, okay, of wrong let me just do this. So I'll show you, so sorry, I'll show you an example on Thursday of this bad reasoning. Okay. But just what I mean here is that if if we are asked to show, let's say, I mean, no, you're not gonna like that. Okay. To show whatever, some equality, you know, n cubed minus, yeah, okay, let's write one which is, okay. A plus b cubed equals to, yeah, a cubed plus 3a squared b plus 3ab squared plus b cubed. Let's say we're asked to show this. Okay. And you start with this and you mess around with it until you get 1 equals to 1. Okay, so suppose, so you do this. You say, okay, a plus I mean, of course, if you develop the left-hand side, you get the right-hand side, but that's not, okay, so if, okay. So if you start with this equality and deduce, say, 1 equals to 1, you have proved nothing. Because what you've proved is that if this is true, then 1 equals to 1. But we know that from anything, from something false, you can deduce whatever you want. It's always true, okay? So it doesn't prove anything, okay? Because false implies whatever is always true. So if I use 0 equals to 1, I'll be able to prove whatever I want. Okay, it might take a long time, but I can prove whatever I want. Any statement, give me any statement, like from 0 equals to 1, I can deduce your statement doing correct reasoning and mathematics all the way. Okay, it might take a long time, but we'll be able to do it. Okay, so if you start with what you're trying to prove and deduce something true, that's a bad strategy. Okay, it just because I mean, you could have started with something false and done the same thing. Okay, it's the other way around. You want it. So I didn't see who.
Yeah.
Yep.
For this example, like if you end up with 1 equals 1, is it wrong because you're just basically just restating the question, you're just saying the same thing as at the beginning? Is that right? I'm not sure I understand.
Okay, the key word here is deduce. Okay, so if I do something like I start with my equation here, and I do if and only if blah blah blah, if and only if blah blah blah, if and only if blah blah blah, and eventually end up with 1 equals to 1, then I've proved it because I've got all the arrows coming back, right? That would be correct. But when I'm saying deduce here, I'm meaning if this, then that, if this, then that. So it's the backward arrows that are important, not the forward ones. So this is, let's say you say this is to be.
If we proved in both ways, like if a plus b cubed equals this in the like it implies the left hand side implies the right hand side and the right hand side implies the left hand side. Would this be good to prove the statement or not?
I'm not sure. Sorry, can you? I'm sorry. What do you mean by left hand, right hand side? I'm not sure.
Like you said if we use if and only if for the proof, it would be good.
Yes.
To show the equality.
It's perfect. So, it's absolutely perfect.
So we could.
That is correct. It's not elegant, but it is correct. Okay. So here's what I'm trying to. So just remove that. Okay. So if you look at what I wrote here, if you start with what you want to prove and you imply stuff, you say, okay, if this, then 1 equals to 1. This is no good. You've proved nothing because starting from what you want to prove, ending up with something true does not prove anything. However, if you say this is equivalent to this, if you prove this correctly, oops, then this is correct. Because you have these arrows going like that, which is exactly, that's what you want. So if you start with something true and you end up with what you want, then you're good. Right? It's the reverse arrows which are important, not the forward ones. I hope I'm not confusing everybody, which I feel I might be doing, but
No, it's clear. Thanks.
The danger with this is that I've seen, and I'll come up with an example for Thursday. I have to find one. It might be a trig identity. I hope not, but okay. But is that the if and only if, you have to really make sure that it is, I mean, it's really the reverse arrow which is important. So if you at any step, it's not an if and only if, you've screwed it up. So it really has to be an if and only if at every single step. Otherwise you can't come back. And that's bad. Okay. So the whole thing will fail. I'll find one for Thursday to show you. Okay. So let's put this aside for now, and I'll get back to it on Thursday, just to illustrate what I'm trying to say with difficulty. Sorry. It just popped into my head as I was doing this, and I wanted to tell you. Okay, here's another example. Prove that the only consecutive positive integers less or equal to 100 that are perfect powers are 8 and 9. And we mean here, in other words, of the form n to the a with a bigger than 1. Okay, because the power 1 is not we won't consider it as a perfect power. Okay, so we look at all the numbers from 1 to 100, and we want to show that the only two consecutive that are actual powers, non-trivial powers, are 8 and 9. Now you can go through. So there's the proof, and there's the way to get it, which there are two ways. You can just list them all, right, and just check, and it's long, it's painful. But there's a quicker way to do it, which is as follows. So here I'm just jumping to the fastest way. So list all perfect powers first. So that'll save you, I mean, less or equal to 100. This will save you a lot of time. So let's start with the squares, right? So what are the squares? There's 1, oh boy, 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, right? Cubes. So I'm just cubing the numbers one after another and stopping at 100. So 1 cubed, 2 cubed, 3 cubed, 4 cubed, and 5 cubed is too big. Fourth powers, 1 power 4, 2 power 4, 3 power 4, and that's it, right? Fifth powers, this will have to stop, right? Because things will get too big. So fifth powers, 1 power 5, 2 power 5, 3 power 5 is too big. Is it? Yeah. Sixth powers, 1 power 6, 2 power 6. That's it. And that's it. These are all the powers between 1 and 100. Okay. So there's nothing else. The rest is, everything else is too big. And now you just look. That's just inspect. So inspection, 8 and 9, that's it. That's the proof. Okay, so not anything fancy, but at least there's this little trick where you can just list the powers first, and you're reducing the number of numbers to consider considerably. Yes. Eh. Let's what time is it? I'm gonna stop soon.
I don't understand the like the question asked in this example. Like, prove that the only consecutive positive integers less or
Between-
equal than 100 are the perfect powers of 8 and 9.
That are perfect powers are 8 and 9. Okay, so positive integers between 1 and 100. Okay, so if you look at all the numbers from 1 to 100, some are perfect powers, some are not. Okay, and we're asked to see that of those that are perfect powers, there's only 2 that are consecutive. That's 8 and 9. Does
I'm not sure to understand.
Okay. Look at the numbers. Okay, so the numbers that I've put on the board here are the perfect powers. That's all of
Yeah.
them between 1 and 100. So list them all. Which ones are consecutive, one after another? Plus 1, I mean the difference of 1. 8 and 9. I mean, you have to look, but that's the only 2 that are one after another.
Oh, okay. But
Yeah.
okay, with cubes and squares.
Yeah, so squares, cubes, 4th powers, 5th powers. These are so a power 2, a power 3, a power 4.
But like the 8 is in the cubes and the 9 is in the squares.
Yeah. Absolutely.
So
Yes.
that's the thing we were looking at. Okay.
Yeah. So we're looking at all possible powers of numbers between 1 and 100, and there are only 2 which come one after another. But yeah, one
Okay.
is a cube and the other is a square. Yeah, yes. They're not.
Okay,
Yes.
thanks.
Okay. Let me do. That's boring. Let me do. Okay, let's do a similar one and then we'll stop. This one is a bit trickier, but that's a cool one actually that touches upon more advanced things if you want to see it, but it's not necessary to know anything not elementary. So we have to show that x squared plus 3y squared equals to 8 has no solution with x, y, and z. There's a very, very, very famous theorem, Fermat's last theorem, which has exactly this form. You're given an equation, and the claim is that there are no solutions in integers. And that's tough, right? Because you have to prove that it'll never work for any integers that you plug in. It's never, ever going to work. But this one has a specific shape that makes it easy. Okay. And the trick is this: just think, what happens if x and y are pretty big integers? Can this be true? Can this equation be true if I put x and y pretty big in there?
No,
No.
because they're going to be
Nope.
squared and they're going to be even bigger than 8.
That's right. So the left-hand side, because of its shape, it's a square plus 3 times another square. So as x and y get big, this thing is getting bigger and bigger, and eventually it'll get bigger than 8. So that's the first hint that this could be easy. It means that you don't have to look at x and y too big. Okay, so first observation. So what I'm doing here is not the proof, it's my scratch paper, right? First observation. X squared plus 3y squared will be bigger than 8 if, and let's say x is 3, then for sure that's over, right? If x is bigger or equal to 3, and it will be bigger than 8 if y is greater or equal to 2. So the minute one of these two guys is, and not even so big, right? But you can forget about all those values. Okay, that's the first observation. Now you say, okay, we're looking at solutions which are integers, so they could be negative. So this could be bad because we could be going infinitely to the left, right? But maybe you see that this is not a problem. Do you need to look at infinitely many solutions or values of x and y? No, because x and y are squared. So if you have a solution, let's say x is minus 72. Well, if x is minus 72, I might as well just put x equals to 72. I'm going to get exactly the same thing, right? So if there is a solution where x or y is negative, I might as well just take it positive. So I don't have to look at negative values for x and y. Let me write that up. Okay, so since minus x, no. Since x and y are squared, right? If there exists a solution with x or y negative, then there exists a solution with x, y positive. Do you agree with this statement? So if I manage to find a solution where one of x or y is negative, I can just flip its sign. I will still get a solution, and then both x and y are positive. So if there's a solution, there is one where x and y are positive. Agreed? Yes.
Yes.
So if I show by the same reasoning, I mean, what it says is if I show there are no solutions with x, y positive, then there are no solutions whatsoever. So hence, if I show no solutions with x, y positive, greater or equal to, let's say greater or equal to 0, then there are no solutions at all. Okay, so I don't have to worry about negative values. I can just look at greater or equal to 0. My first observation says I don't have to look very far. So from these two observations, no, don't. It's going to die. No, what's going on? Okay, so by the above, it suffices to consider x 0, 1, 2 and y 0, 1 only. That's all you need to look at, right? And what do? You plug in the 6 possibilities and you see that there's none of them will work. Okay, then just plug in the 6 possibilities and verify none work. That's it. I'm not going to do it. It's just elementary checking, right? I mean, hidden in this very small baby example is like a very, very important idea, is that suppose you want to check the solutions to some equation with a computer. I mean, if you manage to show that there's only a finite number of solutions, that you'll be able to do it. Otherwise, it's not going to work, right? You need an infinite amount of time to check an infinite number of possible solutions, right? So the first thing, so if you can manage to get it down to a finite number, that's pretty good. If that finite number is too big, that's still not good, but that's a completely different story. much harder. But here you see that the shape of the equation makes it so that the values that you need to check is very small. You just check them and that's it, right? So okay. So what I will do is I'll stop here. Zoom fatigue. And I'll continue tomorrow. I think, I'm not sure I can finish tomorrow, but close. So we'll, in the worst case, I'll finish on Monday, the material for test 1. Okay. Quiz on Tuesday, a little proof, and something from 1.4, 1.5 on first order logic. And I'll try to, yeah, on Thursday, I'll also give you an example of this wrong reasoning. And I'll try to cobble up something giving you the big picture before we move on to something completely different, okay? All right, so any questions, comments?
All good. All good.
Excellent. Thank you. So let's stop this recording.